Superheroes. The name brings images of beings with great power who use them to do good. Dinosaurs. The name itself brings an image of incredible creatures roaming the earth in a long bygone era. So what is cooler than a superhero or a dinosaur? A dinosaur superhero! There is an untapped treasure trove of potential dinosaur superheroes that can be created. One dinosaur superhero is a species so iconic and famous that is the only dinosaur to be called by its whole scientific name, the Tyrannosaurus rex. First discovered in 1902 in Hells Creek, Montana, the T-Rex is one of the largest theropod and carnivorous dinosaurs to have ever existed. With a bite force of 6.5 metric tons, the T-Rex holds the title of the strongest bite of any land animal in history. To put this into perspective, a T-Rex could easily crush a car with its mouth. So what else would put more fear into criminals than a 12.3 meter long and 3.96 meter tall superhero who could easily have you for lunch? And don't you think you could stay still and hide from a T-Rex? T-Rexes had excellent vision, being able to see up to 6 kilometers away, 4 times longer than the human eyesight. However, there is one rather iconic weakness of the T-Rex: its short arms. Although it is now theorized that a T-Rex could bench press over 800 pounds, its 0.9 meter long arms were quite small compared to its body. The T-Rex likely encountered many problems as a result, including catching prey, gathering objects, and pushing itself from the ground by its own arms. With a top speed of less than 17 miles per hour, it has a very slow speed compared to many other animals, which is another weakness. To solve both these weaknesses, we have designed a grappling hook and shooter for the dinosaur superhero. The grappling hook will be connected to a metal cable and will be shot out and reeled back in to allow the dinosaur to be capable of climbing, catching and attacking prey, escaping enemies, gathering materials, and destroying objects, which are tasks that would be much more difficult for a dinosaur with short arms and a slower speed can do. The hook and shooter will be reddish brown to camouflage with the color of the dinosaur itself. We have named our dinosaur superhero G-Rex, which takes the elements of the names of 2 of our engineers, Greeley and Rex. With these enhanced abilities, G-Rex can become a crime-fighting superhero and bring justice to criminals that prey on the weak.
A grappling hook with the means to fight crime and potentially save the world must be strong, resistant to abrasion, hard, and possess a high yield strength. For these reasons, the grappling hook will be metal, as this hook needs to support massive amounts of weight whilst resisting plastic deformation and fracture. A variety of common metals were discussed and evaluated using a design matrix on a number of categories, including yield strength, hardness, resistance to corrosion, fracture toughness, melting point, hardenability, specific heat, electrical and thermal conductivity, and cost and sourcing feasibility. Of the common metals, high alloy steel achieved the highest scores in the majority of these categories. A number of commonly used alloys were then listed and evaluated using these same categories. The selected alloying elements included chromium for its resistance to corrosion, like that of stainless steel, molybdenum to prevent pitting corrosion, nickel to further increase strength, toughness, and resistance to corrosion, vanadium to improve grain structure and shock resistance, and tungsten to provide hardness and strength. The other elements, which include carbon, sulfur, and phosphorus, were used in small compositions because almost all steel alloys use these elements in order to maintain the characteristic properties of steel, such as machinability and improved overall properties and behavior. Thus, a new alloy was born, Jurassite. This high alloy steel incorporates the most desired properties from several elements, but it might come at a higher price and could be more difficult to machine. To further enhance Jurassite, we decided to heat treat the steel, which involves austenitizing, quenching to form martensite, and increasing resistance of dislocation movement. Later tempering, which relieves stresses, refines grain size, and reduces brittleness. The main resulting properties of the heat treatment methods are increased strength, stiffness, toughness, and hardness. A main method of failure is that cracks are likely to propagate from bends in the hooks, sharp corners, or in any scratches. In an effort to prevent this failure from occurring, cold working can be done to further strengthen and harden these areas of concentrated external stress at the bends of hooks. Another specific location of high abrasion in our design is the region that connects the loop of the cable and the top of the hook. To protect this region, we plan to use stainless steel thimbles to prevent abrasion due to the hook and cable rubbing against each other. Because the grappling hook will be exposed to weathering, it is important that corrosion be prevented. This was accounted for in the decision between stainless steel and a regular steel alloy. To further increase corrosion resistance, cathodic protection will be utilized by placing a piece of magnesium over the area and protecting that with a layer of paint. To manufacture the grappling hook, 4 rods of Jurassite that have been heat treated and cold worked will be welded together to form the hook in a perpendicularly symmetric pattern. The hook will then be attached to the cable. Considerable research and calculations were needed for determining the quantitative values of the main properties of Jurassite and the dimensions of the hook. The hook and cable should be able to safely support 5 times the weight of G-Rex, which should be sufficient for quick and forceful movements such as raising himself to the top of a tree or hauling a large object. The maximum amount of stress the hook and cable can withstand is limited by the amount of force the G-Rex can withstand because the dinosaur is ultimately the one bearing the load. Given that the yield strength of Jurassite is estimated to be about 1900 megapascals, we calculated that the circular cross-section of each arm of the grappling hook should be about 13 millimeters in diameter. Also, the elastic modulus is about 190 gigapascals, and the hardness is predicted to exceed 350, thus meeting the recommended hardness for hooks. We decided to use a larger than average size for the grappling hook, about 0.35 meters in height and 0.4 meters in overall width, which equates to a length of about 0.5 meters of Jurassite for each arm of the hook. In order to support the G-Rex's mildly obese weight of 11,000 pounds, we needed not only its trusty hook to be load-bearing, but also its means of extension and propelling via cables. Cranes and heavy industrial machinery operate using high-carbon steel wire cable, which we decided to model for the G-Rex's cable. Strands of rope are spun in a corkscrew-like shape around a pre-existing wire rope. Lubricant is used in this process to act as a facilitator to make sure the wires move smoothly into the die and is used between the wires to increase flexibility and longevity. The wire is then subjected to a series of vertical and horizontal loads by way of metal rollers in an effort to make sure the wires do not become unraveled and to correct its diameter. To further increase resistance to wear and tear, a plastic coating will be added to the exterior of the rope. We decided that the length of the cable would be about 100 feet. The average height of a T-Rex was about 13 feet, so a 100-foot cable would be about 7 to 8 times the height of G-Rex and should be sufficient for most of its climbing needs.